Okay, welcome everyone to this morning's plenary session, which is going to be given by Professor Yiguang Ju from Princeton University. Yiguang is the Robert Porter Patterson Professor in the Department of Mechanical and Aerospace Engineering at Princeton University. He received his BS in Engineering Thermophysics from Yiguang University in 1986 and his PhD in Mechanical and Aerospace Engineering from Tohoku University in 1994. Dr. Ju's research interests include combustion fuels, plasma, and energy nanomaterials. He has published more than 250 refereed journal articles. He is a founding fellow of the Combustion Institute and a fellow of the American Society of Mechanical Engineers. He received a number of awards, including the Distinguished Paper Award from the International Symposium on Combustion, the NASA Director's Certificate of Appreciation Award, and the Frederick William Bessel Research Award by the Alexander von Humboldt Foundation, and the International Prize of the Japanese Combustion Society. And today he's going to talk about understanding cool flames and warm flames. So take it away, Yiguang. Best of luck.
Thank you, Henry, for the kind introduction. Dear colleagues and dear friends, and good morning, good afternoon, and good evening. It's my great honor and privilege to give this plenary lecture. At first, I would like to thank the program co-chairs, Professor Tim Lewin and Professor Fei Qi, for the kind invitation. And then I would like to say that what I'm going to talk in the next hour about cool flames and warm flames is a contribution from many of my colleagues and in combustion. At first, I'd like to thank my colleagues at Princeton for their collaboration and support. Then I would like to thank the people of NASA Microgravity Droplet Combustion for sharing their cool flame data. And then I'd like to thank the colleagues who share their cool flame data for shock tube flames, turbulent combustion, micro reactors, and numerical simulation. And more importantly, I would like to thank those in chemistry who I learned a low temperature combustion chemistry from. Thank you very much. And also, more importantly, I'd like to thank the collaborators in Air Force Research Laboratories and the people who worked with me for a long time and made the original contribution to low temperature flames. Without their work, and it's impossible for me to give the talk today. Thank you and congratulations to your great work. So my talk today, including three parts. First, I will discuss the challenge of low temperature energy on combustion. Then I try to present the cool flames and warm flame to you. Then I discuss the impact of cool flames on engine, fuel, and low carbon energy. And the combustioners today that we are so proud because more than 80% of the world energy conversion today is from combustion. And also we are proud because understanding of fire and create mankind civilization and industrial revolution. See from the picture here that from promise brought fire to the earth, and mankind be able to using fire to make food and to light in the darkness and to kill bugs and for agriculture. And we invented internal combustion engines. We now try to fly hypersonic. It's really proud of the combustion contribution. At the same time, and combustion facing a big challenge. For example, is this a Tesla asteroid impact on Earth will kill the dinosaur of internal combustion engine? If not, what is the game changers for combustioners? So what I try to say is that efficiency and low carbon reduction and low carbon is the key in the future in front of us. If you're looking at the engine efficiency today, here's a picture from Nissan showing that if you have 100 units of energy, and the useful work will be produced in today's on-road diesel engine is only 42%. And more than 50% are either loose from exhaust gas or from cooling. And then the efficiency is far less than the Carnot efficiency and auto efficiency is supposed to be. So what do we have to do? So we have to do that. We have to increase a low temperature combustion, encourage to reduce the heat loss by using lean burn, by using ignition assisted low temperature combustion, such like that HCCI, RCCI, by increasing the compression ratio to improve that thermodynamic efficiency by using constant volume combustion or pressure gain combustion, by using the green fuel to drastically reduce carbon. A good example is that the research from Japan by the Science Innovation Group. You can see in the last 4 years that by using lean burn and engine combustion control, the efficiency was improved from 38.5% all the way to more than 50%. This is great progress. Nevertheless, we have a long way to go. In order to further improve the compression efficiency by using pressure gain combustions and then high compression ratio, so we have problem of control of engine knock and the low speed pre-ignition. And also we have problem that in detonation engines, we have a detonation failure. So the question to ask today is that how do using low temperature combustion and to contribute to the design advanced engines and green fuel. So let's think about from the time scale first. The low temperature combustion, it means from low temperature ignition to a high temperature ignition. The time scale for low temperature combustion ignition is between 0.1 to 1 millisecond, which is equivalent to the time scale of the engine power stroke of a diesel and gasoline engines, and also to the flame burning time. In earlier in 2015, for example, Dr. Skeen made a high pressure a spray injection of endodecane into high temperature air. As you can see from here, the large amount of the formaldehyde is formed at the early stage. So this formaldehyde formation indicating that there's a cool flame chemistry is going on. The Schlieren image showing that near the high temperature fuel lean region, the cool flame start to develop and propagate into the core region of the jet. In comparison to the time scales of different flame regimes in engine conditions, Dames that is showing that the low temperature ignition first occur at the fuel lean conditions, and that the cool flame propagate into fuel rich regions. At the fuel rich region, you have transition from low temperature ignition to high temperature ignition, and then you generate high temperature flames at the near stoichiometric condition, for example. But the question to ask here is that how does the cool flame burn differently from hot flame? So to answer that question, let's start from what is a hot flame. If you look at the textbook about Furman Williams or et al., they will say that flame is exothermic, luminescence, and diffusion ignition flames. What I'm trying to add today is that the flame indeed is a process. You have a chain branching reactions. For example, for premixed flame that you have a beautiful color, and then you have a very thin reaction zone and have a flame speed, and the diffusion reaction controlled. With diffusion flame, you may not have a speed, but it is the same reaction zone, and you have a diffusion reaction control. The key chain branching reaction for high temperature flames is H plus O2, generate two radicals. The time scales in the flames as defined by the time scales of the transport and to the ratio of the time scale of chain branching reactions in terms of Dancur number. A classical definition of flames is that Dancur number is order unity of 1. But ignition Dancur number is 0. That means that the unburned mixture is chemically frozen. With this definition in textbook in combustion, we know that the high temperature flames exist about 1200 Kelvin, has a lean burn limit at the fuel lean region, has a rich burn limit at the rich region, at which the Dancur number is less than 1. For diffusion flame, that the combustion is governed by the flow resistance time. At short flow resistance time, and you have extinction limit, as a stretch extinction, at which there's no time for combustion to occur. At the longer flow resistance time, that you got the bigger flame, and then you have a strong radiation. The radiation will kill the flame. So therefore, a diffusion flame is bounded by a stretch extinction and a radiation extinction. Now, how many flames do we have if we consider low temperature combustion? So if you're looking at the low temperature combustion, let's look at the chemistry first. Look at that, the chemistry reviewed by Henry and Frederick. You can see that at high temperature, about 1200 Kelvin, the fuel basically attacked by radicals and form a fuel radical, which dissociate and form vinyl and H radicals. The H radicals will react with oxygen and generate multiple radicals. This is the chain branching process. In summarizing, at high temperature, you have few radicals and reacting with single molecule of oxygen, generate two radicals. At the intermediate temperature, you have a fuel and a few radicals react with oxygen and form hydroperoxy radicals, HO2. This HO2 react either form a peroxide or react with few radical, and then you form a chain branching reaction of multiple reactions. So in this reaction is also that single oxygen process. However, in a low temperature combustion, the few radicals react with oxygen and form peroxide radicals, but then add another oxygen and generate O2-COH and even dissociate into multiple oxygen. So summarizing, at a low temperature combustion, you have two oxygen process, and that few radicals react with oxygen and then become multiple radicals. So you have three temperature-dependent chain branching reactions. So therefore, which define that you will have three flames. One is that hot, the other one is warm, the other one is low, corresponding differently to the three temperature-dependent chain branching reactions. If you pay attention to this, you will see that at high temperature, the chain branching reaction is only proportional to the oxygen concentration. However, for cool flame, that because of multi-oxygen process, we are proportional to the square of the oxygen concentration, making it different from that high temperature flames. And we ask the question, how would a low temperature flame burn differently from hot flames? So to answer that question, let's start with a chemistry first. If you look at this figure of DME oxidation in a jet reactor by Frederick, you can see that the DME oxidation increased with the temperature initially and then decrease again. This decrease is caused by dissociation of O2-COH radicals we call negative temperature coefficient effect. So therefore, for low temperature flames, the burning rate is not monotonically proportional to that temperature. If we look at the temperature again, this is the ignition delay time as a function of temperature. The solid line is high temperature ignition, the dashed line is low temperature ignition. You can see the low temperature ignition is one order of magnitude shorter than the high temperature ignition. And more importantly, if you have radicals like OH, and then the low temperature ignition can be 2 orders of magnitude smaller than the high temperature ignition, which make that the ignition time can be comparable to the flame burning time. And ignition Dunker number in the combustion is not 0 anymore. So therefore, in classical combustion, we know that the reaction rate is proportional to the flame temperature. We know that the reaction rate is proportional to the oxygen at the constant temperature. We know that the burning rate is proportional to the pressure to the N divided by 2. And we know that the ignition Dunker number is almost 0. But now this will be applicable when you're talking about low temperature combustion. For example, when you have this NTC effect, and that the flame speed will not be monotonic function of temperature. And when you have the multiple oxygen process, the reaction rate is not proportional linearly to the oxygen concentration either. And the pressure, again, and dependence will be corrected by power of alpha due to this oxygen and NTC effect. And the flame speed, again, it will be modified by the ignition Dunker number because ignition is not 0 anymore. And how do we understand this? And by doing experiment and modeling. So let's review what is cool flames and warm flames. And cool flame is not something new. It has been observed 200 years ago by Davy, in which that is air with a vapor of ether. And if heated with a heated metal, you see a very faint luminescence blue flames. In early 30s, that people understand there's cool flames as relevant to engine knock, and also that the blue flames is found in the few rich mixtures. And also that in 30s and 50s, people understand there's an NTC effect. There is a alkyl peroxy chemistry, and there are 2 oxygen addition. So in terms of low temperature combustion. As you can see from the figure before, in a few rich mixture by acetaldehyde with oxygen in a heated reactor, at a low pressure, you can see there's a very bluish and cool flames. As you raise the pressure, the reactivity increases. You see a blue flame and a cool flame and 2-stage flames. This was called blue flame because of the color. But today I will try to change the name is a warm flame. And if you increase the pressure, these 2 flames, they merge together, become a single flame branch. Therefore, from 1940s to 70s, and the research has been focused on the cool flame in rich mixtures, as been summarized in Williams' paper, that if you plot the oxygen concentration as a function of fuel concentration, this is at the lean burn limit of hot flames. This is at the rich burn limit of hot flames. you can see the cool flames exist near the rich limit and no cool flame observed at the lean side. A pioneer experiment in 2000 made by Pillman using a flight experiment in microgravity, and also successfully observed that in a rich propane mixture, and then autoignite and free propagating cool flame can be observed. However, there was no observation about that the lean flames. What we understand that before 2000, cool flames and warm flame observed at very few rich mixtures. However, today that the combustion, our interest is low carbon energy. We want to burn few lean or is very highly lean mixtures. And what is that the cool flame and rich flame, warm flame dynamics in the lean side? So in 2010, you can see that the Kaoru Maruta in Japan, and they conduct experiment is heated microtube and using dimethyl ether air mixtures. And what he found that by raising the pressure, you can see that hot flame and then a multi-state flame at the stoichiometric conditions. At the same time that we conducted that modeling about spark-assisted HCCI. With the spark creating a very high temperature flame front. As the time going, this flame front decomposed into two, a leading cool flames and a trailing hot flames. It's not clear at that time whether that this kind of double flames will really exist in laboratory. At the same time, for non-premixed mixtures, the question we want to ask is that, what about the non-premixed mixtures? Do we have cool flames in non-premixed mixtures? Here is the early computation by Peng and my colleague at law, showing that at high pressure for non-premixed flame, you have this kind of a folded S-curve, suggesting that you might be able to see a cool flame in non-premixed mixture. So to observe that the premixed cool flames, and at Princeton, we're using ozone sensitization and try to see that the flame transition from hot flame to cool flame. As you can see that by reducing that let me play it again. It doesn't work. But by reducing that the fuel concentration, a hot flame will reduce into a double flame with a lean cool flame in the front with a hot flame in the back. And then for the reduced fuel concentration, only cool flame can exist. So this experiment proved that the computational modeling of a double flame actually can be observed in an experiment. And the question to ask here is that what are the flame regimes in terms of lean cool flames? To answer that question, and we conducted the computation of dimethyl ether at 1 and 20 atmosphere pressure. And we know that classically that hot flame exists between these two limits. And then at the rich side, we have a cool flame and warm flames. On the lean side, the modeling tells us that you have a lean cool flame on the lean side as well. And also interesting, you can see that the lean cool flame is non-monotonic here, and the rich side is monotonic. And you may ask why. And the reason is because from the chemistry. At the lean cool flames, you have very high oxygen concentration, and the reaction rate is proportional to the square of that oxygen concentration. That generates a lot of HO2 radicals, and then heat release. That HO2 radicals branching, and then the heat release trigger that autoignition of cool flame directly to hot flame. That's why that is monotonic. And between the cool flames and hot flame, what you see that there's a double flame forming between the hot flame and the cool flames. And with this flame is not stable if you don't have heat loss or radical losses. If you further increase the pressure, that you know that the fuel radical concentration and HO2 will increase. This leads to the chain branching reaction of the warm flames. So you see that a warm flame is existing between the cool and hot flame at the rich mixture. So summarizing what the result, we can see that we have a hot flame that convert that fuel into water and CO2. We also have a cool flame that convert that reactant into aldehyde, CO, and peroxy. And the double flame is a combination about the cool flame and the hot flame. They all convert that reactant to water if there's enough time. However, the warm flame is that you have a cool flame front and with a distance about delta CH, and you have a intermediate temperature flames. This flame only convert that the aldehyde into CO, not into CO2. And if you look at the warm flame structure, and it is that you have a heat release rate. You have two heat release. First is the cool flame heat release. The other one is the intermediate temperature flame. And the distance between them can be millimeters to centimeters. That dramatically enhance the coupling between flow and then warm flames. Here's the picture of different flames. We don't have a warm flame, a lean warm flame observed in the lab. It's because that we don't have the image yet. I hope one of you can share with us in the future. So what is a warm flame, for example? If you're looking at N-heptane warm flame, so you have two states, is a cool flame and you have intermediate flame. If you do a computational singular perturbation analysis, you will see that in the front of the cool flames, you have explosive mode that generated the QH radicals. You also have the active mode that generates heat and then isomerization of alkyl radicals. For that intermediate flame, you don't have explosive mode, you only have active mode. This is that the few radicals with H2O2 reaction generate two radicals. They govern that the warm flame chemistry. If you compare that the timescales of diffusion and reaction, you can see that in the cool flame that the two timescales are comparable. So this is that the reaction diffusion controlled structures. However, for intermediate flames, you can see that the reaction timescale is always faster than the diffusion. So therefore, the warm flame is not a typical reaction diffusion controlled structures. It is autoignition assisted flames. If you're looking at how does that the cool flame speed depend on pressure. So this is that normalized temperature and normalized flame speed. As you can see that with the increase of pressure, that the hot flames and the rich cool flame, the flame temperature does not change much. However, the lean cool flame temperature will increase dramatically. We know that the reactivity is proportional to the temperature and oxygen concentration for the lean cool flames. However, with NTC effect, will slow down dramatically that the speed of lean cool flames, even make it slower than the hot high temperature as with the increase of pressure. Interestingly, on the feed rich side, you can see the flame speed barely change with the increase of pressure. This is because there's no NTC effect, while with the increase of pressure, the reactivity increases as well. So what I summarize that in cool flames, you have the mass burning rate, not only proportional to the pressure to the reaction order, but also you have to correct it by alpha. This alpha due to that oxygen and NTC effect. For lean cool flames, alpha is less than 0 because it has strong NTC effect. However, for rich cool flames, the alpha is larger than 0 and less than 1 because there's no NTC effect. And then the reactivity increase with the pressure. Unfortunately, there are few experimental data available of the cool flame speed at high pressure. This is the only data available for very low pressure of cool flame speed. So if you plot the burning limit of different flame regimes, this is the pressure as a function of equivalence ratio. So this line, the BAB, is that the lean burn limit of hot flames. That means hot flame exists on the right and the region 1 and the region 2. The double flame exists only in the region 2 at a lower pressure. And then the cool flame exists in below that hot flame and also in the region 2. So therefore, in region 2, you have 3 kinds of flames: cool, double flames, and hot flames. And as the pressure increasing, that fuel radical concentration increase, and you will see that there's a warm flame start appear and in this region at high pressure. So this diagram gives a generic understanding. Where do we see warm flames? In some regions, you have multiple flames. You need a multi-physics computation to make a correct prediction. What about the diffusion flames? Let me show you that this is a pioneering experiment of microgravity alkane droplets. When your hot flame initiated here, as the flame radius increase, the radiation increase. As the radiation increase, radiation extinction occur, and you form a cool flame, which continue to decrease at the diameter of the droplets. And on ground experiment, by using plasma heated air and using ozone sensitization, at Princeton, we will successfully observe this kind of cool flames as sustained in the counterflow flow. And by further using the ozone sensitization with dibutyl ether, for example, we can see a warm flame. You can see on the fuel side, there's a cool diffusion flame. On the oxygen side, you have intermediate temperature flames and diffusion flames. So we wonder that at what condition a cool flame can exist, what flame that a warm flame exists. Here's a diagram showing you the flame temperature as a function of flow resonance time. you can see that the hot flame only exists at high temperature and is bounded by a stretch extinction limit and radiation extinction limit. And below this, you have a warm flame and have a cool flame. This diagram shows that if the flame radiatively extinguished, they can move to a warm flame and then drop to a cool flame. You have a smooth transition between three flame regimes. This is an experiment conducted by NASA, a Flex 2 alkane experiment. It's showing you that the ignited droplet with the increase of flame radius, you have a hot flame. That hot flame eventually transitions to a warm flame, and the warm flame becomes a cool flame. That experiment confirmed that there are three different regimes of diffusion flames, and then they can transfer between each other. If you plot the regime diagram in terms of flow residence time, or the oxygen concentration or fuel concentration, the hot flame is bounded by two limits, that the stretch extinction at a short residence time, and then radiation extinction at a longer residence time. And then this O is the burning limit of hot flames. Where is the warm flame? The warm flame will be in this region. They can burn at a longer flow residence time in the hot flame at a high oxygen concentration, but they also can burn in a region that a hot flame cannot burn. And the warm flame exists below this because that have a larger heat losses. So in some region, you can have three different kinds of flames also coexist in a non-premixed mixture. And then that both cool flames and warm flame can burn much leaner than the hot flames. So then we try to understand the question that what is the reaction order of the cool flame dependent oxygen? So this is that experiment from a NASA group and showing that the normalization of extinction droplet diameter by the representation rate with different alkanes. So the average N will be N equal 1.5, less than 2. Why? It's because that is the NTC effect. When you have high oxygen concentration, the flame temperature is increasing, they suppress the reaction rate. So this is why the N is less than 2. And at Princeton, we recently conducted an experiment showing for different kind of C7 to C12 alkanes, which plot that the extinction limit as a function of oxygen concentration. We obtain that the N number for different alkanes between 1.6 to 1.9 is bigger than the average value by the NASA droplet coefficient. Why? It's because that the cool flame temperature here is lower than the equilibrium temperature of this NTC reactions. So therefore, less NTC and higher N in our experiment. And how do we control cool flames, for example? Here, experiment between collaboration between Nancy and Princeton with Oliver and Hal is showing that with ozone addition, that the cool flame can be dramatically delayed, but the NTC and intermediate temperature is accelerated. Because at low temperature, the RO2 radicals reaction with NO and they form at RO that suppress the chain branching reaction. At the intermediate temperature, the NO and NO2 will convert HO2 to OH by form NO2 and HONO. To confirm this one in the flame experiment conducted at Princeton showing this is a warm flame as a function of flame temperature, as a function of strain rate. Without NO, you can see this is a cool flame and this is a warm flame at a hot flame. With a NO addition, you can see that the cool flame is flammable region is very narrowed, and the warm flame is shifting to higher strain rate, indicating that NO inhibit cool flames and promote warm flame, and also accelerate the transition between warm flame and ignition. So therefore, NOx is an important sensitive chemicals to control cool flames. And recently experiment between my graduate student Eric Rosso and Niels showing that this is by adding ozone into a long chain alternate fuel, you can see that normally you can see this low temperature reactivity with a methyl hydroperoxide formation. But with ozone, you can see that at even below 550 Kelvin, you can see that this methyl hydroperoxide formation at the extreme low temperature chemistry. And also at the University of Tokyo, that Professor Suzuki and Dr. Lee showed that if you change the surface reactivity of wall by replacing the quartz by iron and the platinum, you can see that by iron surface, the cool flame is shifted to 500 Kelvin. By using platinum, the cool flame can shift it smoothly to 500 Kelvin or below. So therefore, that the wall reactivity play a big deal in control cool flame as well. So summarizing what we found in last 10 to 15 years from 2010. From 2010, that in premixed flame, we identify that there's a double flame, there's a cool flame, there's a warm flames. And for diffusion flame, that we also identify that there is a cool flame, there is a double flame, warm flame, and there is a hot flame. So therefore, there are three kinds of flames: cool, warm, and hot. If you look at the artist plot this picture, you can see that the artist is showing that there are three colors as well: in the red, and white, and then yellow. It seems like that the artist knew that there are three kinds of flames better than us. And then what is the implication about these flames to engines and fuel? So in engines that compression ignition engines, the ignition down current number is much, much larger than 0. So recently experiment by Ron's group in Stanford showing that at high temperature, and the ignition can form this kind of dual flame shape, and the flame speed is no longer monotonically dependent on the temperature and cannot be explained just by high temperature, even that the flame trajectory is indicated by the OH star. And Jackie and my student, Ken Han, and show that the flame speed, by considering low temperature chemistry, they non-monotonically depend on the temperature. You can see these figures. Can this cool flame speed explain this experimental phenomenon? But however, that by computing that the cool flame speed is far below that experimental data, even with increase of down current number. So what is going on? So in order to understand this phenomenon, we compute a numeric simulation from the spark ignition to flames. We can see that there are 5 stages of flames. The first is the ignition kernel, and the second is a double flame that is have a cool flame in front and the hot flame traveling. And 3 is that the cool flame to hot flame unsteady transition. The 4 is a hot flame here, and then 5 is high temperature ignition. By using this double flame regime, you can successfully recompute that experimental data about in the shock tube. And you can see that the high temperature chemistry does not predict correctly about flame speed. Not only that the flame speed is different and in cool flames, but also that the minimum ignition energy and is different too. Here's the result of Penn showing that the low temperature ignition energy, minimum ignition is much lower, and the flammable region is much broader than the high temperature flames. And if you look at that flame stage, that the cool flame Mach-Stern length compared to the Mach-Stern length of high temperature is also different. So therefore, we have to be very careful, cautious, to consider that the dynamics of flames, ignition energy, and the stress are all different in cool flames. So what about that the ignition down current number effect on the flame speed? Because that in this RCCI, in the flame stabilization in cavity, the flame speed is a function of down current number. And how do we do it? And so let's think about that. If you have a mixture, and you have auto-igniting and raise the mixture to a TP. And after that, you have a flame. And in the flame, that you have auto-ignite and become temperature. If you divide this, become a convection diffusion reaction front, you do a symptotic analysis, you will find that flame speed is that the classical flame speed we measure with the down current number equals 0 and normalized by the ratio. Here that you can see the auto-ignition temperature minus that the TP is that the ignition assisted temperature rise. If that the TP here is equal to the auto-ignition temperature, then flame speed will become infinite. And this TP is dependent on the down current number. By plugging in this, you can predict that the flame speed, normalized flame speed, now is an exponential function about the ignition down current number. And that is strongly dependent on about the chemistry as well. So now we have an equation that can predict what is that the flame speed with the increase of down current number. So what about the turbulent combustion? A lot of people talking about turbulent combustion because they have 2 sickness, reaction zone sickness and then preheating sickness. And normally in normal conditions, the reaction zone sickness is even smaller than the Combe scale. So therefore turbulence cannot penetrate the flame sickness. However, for cool flames, you have the very thicker cool flame thickness. And for warm flame, that the distance between the leading cool flame and the intermediate temperature flames, and this can be millimeters or larger. and that can even bigger than the Taylor's microscale or integrated scale. So therefore, it's very sensitive to the flow perturbation. So here showing you the experiment collaboration with Air Force Research Laboratory, showing that if you have a double flame, if you impinge a little bit of voltage, you can see the double flame will be extinguished, become a cool flame. And the cool flame can also extinguish, eventually disappear. You can see there's a rich phenomena for low temperature combustion due to that strong coupling between flow and then the flames. So what about the turbulent combustion? Yeah, at Princeton, we developed this reactor-assisted turbulent slot with a flow reactor in the bottom, and in the top, we have a Bunsen flame. As you can see that by measuring the temperature, a turbulent flame speed as a function of a flow fluctuation. This is that the low temperature chemistry does not play any role. So you can see this is a classical turbulent flame speed curve everybody has been measuring. However, if you consider that the low temperature chemistry, like formaldehyde here, the flame speed is higher than the conventional turbulent flame speed we measure in chemical frozen flow. And more interestingly, by controlling that the ignition Dunker number of cool flames, the turbulent flame speed can be anywhere between this curve. Therefore, with low temperature ignition happening in advanced engines, there's no finite number of turbulent flame speed. It can be anywhere between these two curves. And further collaboration with AFRL, with my colleagues here, you can see that by controlling the low temperature ignition, that this flame can flash back into the burner due to the ignition-assisted combustion. And what about detonation? Detonation is a coupling between ignition and shock waves. So here I show you that the experiment done at Princeton a few years ago with and without ozone sensitization for acetylene mixtures. You can see with ozone sensitization of ignition to detonation transition is dramatically accelerated. If we look at that recent result by Karin, showing that the turbulent flame speed as a function of time. So when the turbulent flame speed becomes comparable to the sonic speed of reactant or the product, you have a strong coupling between shock wave and autoignition. What if we have a low temperature chemistry and sensitized by ozone? Here is that experiment at Princeton. I'm showing that with DME and ozone, with DME oxygen mixtures, and you can see this two-stage spike. We are wondering that whether that the first stage and second stage corresponding to that low temperature impact. We don't have a conclusion yet, but we are excited looking forward to understand it. So for turbulent diffusion flames, Jackie and her group did a lot of studies about that a high temperature fuel jet into a high temperature air environment. As you can see from here, endodecane, you form a lot of hydrogen peroxide, indicating a strong low temperature combustion burning. Interesting is to look at this figure that you have ignition delay time, you have mixture fraction. For high temperature flames, you can see that the ignition kernel develop near the stoichiometric conditions and near that the shortest high temperature ignition condition. However, for cool flame, that the short ignition temperature is here, but the ignition kernel developed at the far richer conditions is different from that short ignition delay time location. In turbulent cool flame experiment at Princeton, Michael Miller and my student collaborate, you can see that here's the measure that the temperature with condition of mixture fraction. You can see that the peak temperature is located at the field link conditions compared to stoichiometric conditions. If you model that the cool flame peak temperature location in a countable flame, you can see that the peak temperature can transfer from rich conditions to link conditions, depending on the local strain rate. So therefore, different from high temperature flames, cool flames ignition and flame locations are not at the stoichiometric conditions. So how does the cool flame provide a platform for chemistry validation? Here I show you a figure for N-alkanes from C7 to C12. This is an experimental result is model prediction and experiment for high temperature flame. They agree pretty well. This is the experimental result of cool flame extinction. This is predicted. You can see that the model does not capture that the experimental data at all. And even for that dimethyl ether, a well-studied mixture, you can see the model basically predicts anywhere several times higher than that the experimental data. And although these models, it can predict reasonably well that you see that this ignition delay time, the flame speed, they do very good job. Why they cannot predict that the cool flame speed? Because all this ignition delay and then high temperature flame speed, they have no constraint in terms of heat release of cool flames, which is associated with large alkanes and their radicals, which is not constrained in a model about jet reactor and shock tubes. So therefore, cool flame provide a new platform to develop a new model, for example, HP MAC and this can predict not only that the ignition delay time, but also that the cool flame extinction. So summarizing that, previously we have shock tubes, RCM, JSR to validate chemistry. We have nominal flame speed to validate constrain our model. But now we have cool flames. We have this shock tube cool flames. We have droplet diffusion cool flames that provide new data to validate that the reactions. So next question I'm going to ask is that how does the cool flame help that the fuel screening? For extinction limit, and extinction limit is a function of transport and the ratio of heat release normalized by heat losses and multiplied by the reactivity. If you define that factor as the transport weighted enthalpy, and this is the radicals, and you plot that the extinction limit of the transport enthalpy for high temperature flames, you can see all alkanes, they form to the single line because the high temperature reactivity are the same. But aromatics with a different molecular structure, they have a different gradient, means they have different radical index. We can use to ranking all the fuel by defining N-heptane has a high temperature radical index is 1. We can, for different alternative fuels, we can rank them by using a radical index for high temperature flames. Recently, that experiment by using a transport weighted enthalpy for cool flames. And we can also correlate that the extinction limit and the transport enthalpy by defining the gradient as a radical index. We can see that for C12, C10, C8, C6, we have a radical index between 0.8 to 1. We define endodecane as the cool flame radical index is unity. So therefore, that cool flame extinction provide a new platform to fast screening that the low temperature reactivity of alternative fuels or green fuels. So what are the applications in terms of cool flame to engine control? So advanced engines is always low temperature ignition assisted combustion. So therefore plasmas, ozone, and NOx chemical additives surface, as we speak before, they all affect that the burning rate and ignition delay time of low temperature combustion, so that allow us to control and HCCI, RCCI. A paper by Philippe Dagal many years ago showing that ozone addition into engine actually changed that the combustion characteristics. And also for lean burn engines and low speed pre-ignition engines and even detonation engines, it's important that how do we control that the coupling between that the pressure waves and the ignition. So thus a control of cool flame play a big role in terms of control the combustion engines. And then as I demonstrated before, and to develop that the engine and fuel co-optimization, and then the radical index provide a convenient tool to fast screen that the green fuel. And recently that in Germany, and Professor Bohock, Atakan, showed that you can use an internal combustion engine to make a new chemicals. And this figure showing that the fuel rich and the ozone addition, you can convert that the hydrocarbons or methane into alcohol. And so this at the fuel rich condition clearly is that these low temperature combustion assisted fuel conversion. So therefore low temperature chemistry can play a role in polyfuel generation. And also recently at a collaboration between Princeton and Stanford and University of South Carolina, and we funded by NSF to study that using plasma to activate that the fossil fuel and CO2 and water, and to control that low temperature chemical process or make it into fuel. This low temperature combustion can contribute to that fuel conversion and chemical manufacturing and towards low carbon energy world. And more importantly, the recent collaboration between us and Niels Hansen and Aaron Jasper at Sandia, showing that the ozone reaction with unburned hydrocarbon VOCs, they create this creaky intermediate. And this creaky intermediate can insert into different molecules, like water, like acid, like formaldehyde and alcohols, and make that molecule bigger and bigger and bigger, and eventually form a particle like aerosol. So therefore, this low temperature combustion chemistry can contribute to the understanding about aerosol formation from unburned hydrocarbons at atmosphere. So this opened a new research area about the low temperature combustion and chemistry. And everybody talking about the battery. And the battery actually was invented by Sony in the 1990s, as you can see from here. In order to increase that battery energy density, today that we are moving to a high energy density electrode, which called high nickel electrode. And nickel is a catalyst. And then high nickel electrode, and it's not stable to stabilize the oxygen. So therefore, there's a strong function about reaction between electrode and electrolyte and solvent. And then this figure basically showing that the presentation at this symposium from our group, showing that by doping some kind of materials like DY into a high nickel electrode, you can suppress that the oxygen release from the electrode. You can also suppress that the autoignition and of the between the electrode and then the electrolyte. So therefore, low temperature combustion, again, understanding the low temperature oxidation, open a new research frontier to that electrical vehicle, electrode, and the solvent. I'm coming back to ask you a question that is combustion research ending, and will that the Tesla battery play like asteroid and kill that the dinosaur of internal combustion? But my answer is that no. So my answer is like this. Look at that. I try to show you that this is that the Wheatstone S-curve, which is that the confidence of mankind and as a function of the knowledge we have. When people gain knowledge, they become overconfident and even become stupid when they're peak of the knowledge. And then you look at the valley and say, oh, you know, nothing can be done. Until that they pass this despair valley, and again, they become smarter, and then they feel happy and then have more innovation. So in combustion, we are in the stage about this kind of NTC curves. For many years, people only worked on high temperature flames. And as the research progressed and people understand almost everything of high temperature flames, except the soot and NOx, two complicated things. And then people feel that we understand everything and start to despair and saying there's nothing to do in combustion. However, as you can see that when you go to a passes NTC and you look at the cool flames, low temperature combustion, you open a new world that combustion is really cool. And we could create this a combustion webinar and try to report that the progress in this area. And stay tuned. So let me talk about one. Thank you very much, and adding one slide in terms of what is the opportunities about the cool flames. And really, we need data at high pressure, and particularly that the pressure and engine pressure. And we need that the cool flame studies really at spray conditions, because that the vaporization and then the pressure and the oxygen dependence in spray combustion is different from gas phase. And also we need to see that as the Katarina presented on Monday at her plenary talk, hotel talk, that you have multiple NTC regions. How does this multiple NTC regions that is going to be affect that the transition between cool flames to warm flames and from warm flame to hot flames? This is unknown research. And also that the multiple oxygen, if we go to high pressure, there could be reaction rate could be the cubic or even hydropic, and depending on oxygen at extreme pressure. And as shown by the work by Jiandong Wang and Sarmani Sarasi, this is indeed an explored area and very interesting to study. And And then you can, so also they open a lot of opportunities in terms of chemistry and diagnostics. And I try not to talk a lot about this. I try to end here so that I have some time with interact with the audience. If I have any question, I can answer one or two. Thank you very much. And thank you, Henry, for chairing my session.
Thank you very much for giving a very nice presentation. And on behalf of the Combustion Institute, we want to present you with a certificate of appreciation for your talk.
Thank you very much, Henry. Thank you for that, the program organizers and the chair. This is a wonderful opportunity and for us to present something about the work of a large group, not just my work, is many work from distinguished groups. Thank you very much, Henry.
Yeah, thank you. Thank you, Yiguang.
Bye-bye. Thank you.
Bye.